All right, welcome. Today, we're going to dig into a question that, well, literally holds up our entire world. How does the ground under our feet actually support everything? From a regular house to a massive skyscraper? The answer lies in something called Terzaghi's bearing capacity theory. I mean, it seems like a pretty simple question, right? But the answer is this fascinating mix of physics, geology, and some really brilliant engineering. Why is it that solid ground can sometimes act almost like a liquid when it's under extreme pressure? And what's the mathematical secret that keeps our cities standing tall? Come on, let's break it down. So to get to the bottom of this, here's our game plan. First, we'll look at the ground's actual breaking point. Then we'll meet the guy they call the father of soil mechanics, Terzaghi, and explore his big idea. After that, we'll get into how soil actually fails, look at the three pillars that give it strength, and finally, see how engineers take this core formula and adapt it for the real world. Okay, so every single structure puts a force on the ground. The huge question for any engineer is, what's the absolute maximum load, the ultimate bearing capacity that the soil can possibly take before it just gives up? And when soil fails, it doesn't just get squished, it actually breaks apart and slides. That's what we call a shear failure. Now, it's important to note that the theory we're talking about today is specifically for what we call shallow foundations. And the rule of thumb is really simple. If the depth you dig down is less than or equal to the foundation's width, you're dealing with a shallow foundation. And that covers a ton of the buildings we see every day. So, to really get how we calculate this breaking point, we've got to talk about the person who first cracked the code, Terzaghi. He's known as the father of modern soil mechanics for a very good reason. His work gave us the very first reliable way to solve this problem. It was back in 1943 that Terzaghi published the first complete theory for this. Now, to make a super complex problem solvable, he simplified it. He focused on what's called a strip foundation. Just imagine the long, continuous space you'd find under a big wall. And that single idea became the bedrock for the entire field of geotechnical engineering. It's a huge deal. Okay, this is where things get really cool. See, Terzaghi didn't just invent a formula out of thin air. First, he had to visualize exactly what is happening in the soil when a foundation fails. He figured out it's a three-part mechanism. So the key takeaway here is that a soil failure isn't just some random collapse. Nope, it's actually a predictable geometric event that happens in three distinct zones right under the building. So here's how it plays out. First, a triangular wedge of soil right under the foundation acts like a solid block and gets jammed straight down. Then, this wedge shoves the soil next to it outwards along these curved spiral paths. These are called the radial shear zones. Finally, all that sideways force pushes two last zones of soil up and out, making the ground surface next to the building actually bulge upward. The best way to picture this whole thing is to think of a snowplow. The foundation is the plow, right? That central wedge is the snow getting pushed straight ahead. And those radial and passive zones? That's the snow shearing off to the sides and piling up in banks on either side of the road. It's a perfect analogy. So, if that's how the ground fails, then how do we calculate the force it takes to make it fail? Well, Terzaghi built his legendary equation by identifying three key sources of strength in the soil. You can think of them as the three pillars that hold everything up. Pillar number one is cohesion. Just think of it as the soil's natural stickiness. It's like the glue that holds clay particles together. It gives the soil some built-in strength even when there's no pressure on it at all. The second pillar is the surcharge. This is really just the weight of all the dirt that's sitting right next to the foundation. The surrounding soil acts kind of like a clamp, putting pressure on the failure zones and making it harder for them to get pushed upwards. And the third pillar is simply the weight of the soil itself, specifically the weight of the soil inside those failure zones we just talked about. I mean, to make the ground fail, you have to physically lift and move this huge amount of earth, and its own weight fights back. So, you put those three pillars together, and bam! You get Terzaghi's ultimate bearing capacity equation. You can actually see each pillar right there in the formula. The first part is for cohesion, the second is for the surcharge, and the third is for the soil's own weight. But what are those N letters that are multiplying everything? Yeah, that's the million-dollar question, isn't it? These aren't just random letters. They are the absolute secret sauce to this whole thing. Let's take a look. They're called bearing capacity factors, and you can think of them as amplifiers. They take the three basic soil properties and they crank their contribution to the total strength way up. So what controls how big these amplifiers are? It all comes down to one critical property, the soil's internal friction angle. It's basically a measure of how well the grains of soil lock together and resist sliding. And this table just shows their power perfectly. Look at this. If a soil has a friction angle of 30 degrees, the N factors are, in the 20s and 30s. But if you just increase that angle by 10 degrees to 40, which seems like a small change, the factors absolutely explode. They jumped over 80, even over 115. That's the whole secret right there. A soil with more internal friction isn't just a little stronger, it's exponentially stronger. Now, remember, this whole thing was originally figured out for that simplified case, the long, continuous strip foundation. But what about the real world? Where we have square footings for columns or circular bases for big tanks. Well, the beauty of this theory is just how easily it adapts. The elegance here is just its adaptability. For a square foundation, you basically just multiply the cohesion part by 1.3 and tweak the soil weight part a little bit. For a circular one, the changes are pretty similar. The fundamental three-part structure of the equation stays exactly the same. It just proves how powerful and robust Terzaghi's original insight really was. So there you have it, a theory that was dreamed up back in 1943, all based on visualizing how a wedge of dirt moves, is still the invisible mathematical foundation that lets us build our modern world with confidence. It's just a beautiful example of a complex reality being described by a simple, elegant, and powerful idea. And that kind of leaves us with one last thought to chew on. If something as messy and seemingly chaotic as soil can follow such precise mathematical rules when it's under pressure, what other invisible forces are out there, quietly holding our world together, just waiting for us to discover them? Thanks for watching.